Mainly, we are going to talk about data representation and numbering system. So, this topic is very much important in order to understand bitwise operators. Okay. So, all of us know about decimal system. So, for example, let me consider one digit. Let's say the digit is like this: 5478, right? Then how to represent this digit, and again I am considering base 10. What is the meaning of this base 10? We need to understand what is the meaning of base first. So whenever I am talking about any numbering system, then base will tell us which digits are allowed. For example, whenever I say that I am talking about base 10, that means digits from 0 to 9 are allowed. So in general, if I am telling that I am talking about number system with base b, then I will be allowing numbers starting from 0 to b minus 1. So in total, I am allowing b different numbers, but numbers will start from 0. So therefore, it will go up to b minus 1 only, right? So that's the idea of this definition of base. So now I'm talking about decimal number system. So decimal means base 10. So whenever I say base 10, that means 10 different values are allowed. And again, like I mentioned just now, numbers will start from 0 and it will go up to b minus 1. And in the case of decimal number system, value of b is 10. So therefore, will go up to 9. So only digits from 0 to 9 are allowed. Okay. So similarly, in future, whenever we talk about base 2, then 0 to b minus 1, which is nothing but 1. So that means 0 to 1. So that means only 0 and 1 are allowed whenever I talk about base 2 system or binary numbering system. Right? Okay. Let's continue. So whenever I talk about some number, let's say 5478, then I know that the place value of 8 is 8 only. So I can write like this: 8 into 10 raised to 0. Now if I talk about 7, then I know that the place value of 7 is actually 70, which is nothing but 7 into 10 raised to 1. Whenever I talk about 4, then I know that the place value of 4 is actually 400, which is nothing but 4 into 10 raised to 2. And whenever I talk about 5, then place value of 5 is 5000, which is actually 5 into 10 raised to 3, right? And so on. So that means in the base 10 system, what I am doing, every time I go from left to right, I am increasing the place value by power of 10. So initially it's 10 raised to 0, then it will go to 10 raised to 1, then it will go to 10 raised to 2, then it will go to 10 raised to 3, up to. And let's say I have n digit number, then this the last value uh, will have this index, which is nothing but 10 raised to n minus 1. Fine. So this is nothing but how we are used to with our generic base 10 system. So a few more terminologies, right? Whenever we talk about least significant digit, then least significant digit in this particular example is nothing but 8, the number which is appearing in the rightmost manner, right? In the rightmost location. That is nothing but least significant digit. So in this particular case, least significant digit is 8. Alternative definition is number whose place value is minimum, right? It's called nothing but least significant digit. And the most significant digit will be nothing but the leftmost number, right? So leftmost number in this particular case is 5. So that is nothing but most significant digit, right? So these are some important definitions. Now, similarly, we can talk about binary number system also. In the case of binary, the place value will be multiplied by power of 2, right? So initially it will be 2 raised to 0, then it will be 2 raised to 1, then 2 raised to 2, up to 2 raised to n minus 1, right? Similar terminology. So, and the major difference is now we are allowing only two digits, 0 and 1, right? Because the base is 2, so therefore we are going to allow only 0 and 1, right? So let's consider one example. Let's say one number in base 2 is this, right? 1011. Then what will be its equivalent value in base 10? We are interested in this. Then what we need to do, again, we know that this is nothing but my least significant bit, and least significant bit must be multiplied by 2 raised to 0. The next bit is nothing but 1. So that must be multiplied with 2 raised to 1. The next is 0, that can be multiplied with 2 raised to 2. And the last bit is nothing but most significant bit, we can say. It's nothing but 1, and it will be multiplied by 2 raised to 3. And if I simplify, then I will get 11, right? So 11 in base 10 and 1011 in base 2, right? That's the idea. Similarly, we can talk about one more example, 10110. Again, we will follow the same tactic, right? So idea is least significant bit will be multiplied by 2 raised to 0, and later on we are going to increase the power of 2, right? And if any number is the actual value is 0, then it doesn't matter whether we are multiplying with it with 2 raised to 3 or 2 raised to 5, right? The overall answer will be 0 for that particular term, right? And so on. Now the next, so this is nothing but conversion of any base 2 number to base 10, right? And it's fairly easy. All we need to do is we need to apply this particular equation. That's it. Now, again, let's consider some terminologies with respect to computer science. So in computer science, 2 raised to 10 is called kilo, right? It's not thousand. 2 raised to 10 is 1024, right? And 1024 is called 1 kilo, right? And usually we hear a lot of terms like this, right? 1 gigabyte, 1 terabyte, 1 megabyte, right? So what is the meaning of all these terms? Let's understand. The first is nothing but the smallest memory unit is nothing but it's called bit, right? So binary digit is nothing but bit. It can be 0 or 1. If you combine 8 bits, right? If you make a group of 8 bits, then it's called byte, right? And now what you are saying, let's say you are talking about 2 raised to 10 bytes, right? 2 raised to 10 bytes, it's nothing but it's called 1 kilobytes, 1 KB memory, right? We know this term, right? 1 KB. And then we talk about 2 raised to 10 kilobytes, then it becomes 1 megabyte, right? 1 megabyte is nothing but 2 raised to 10 kilobytes. And similarly, if I say 2 raised to 10 megabytes, then it's nothing but it's 1 gigabyte, right? And if I say 2 raised to 10 gigabytes, then it's nothing but 1 terabyte, right? So these are the terminologies. So now I hope it's clear. Whenever we talk about memory of hard disk, we talk about gigabytes, right? So what's the meaning of this gigabytes, right? 1 gigabyte is nothing but 2 raised to 30, 2 raised to 10 bytes is nothing but what we say 1 kilobyte, right?
1 kilobyte.
Right. So 2 raised to 10 times 2 raised to 10. After doing this, we will reach to where? Megabyte. And one more time 2 raised to 10. So basically 2 raised to 30 bytes is nothing but 1
Gigabyte.
gigabyte. Okay, fine. Now, in general, we can extend our definition. Let's say if we are talking about base system R, then this will be the notion, right? What we need to do if we want to convert any base system R to, let's say, base system 10, then we are going to use this particular expression. For example, whenever we talk about color system, let's say the number system which with base 3, then only 3 basic colors will be used, and those colors will be corresponding to 0, 1, 2, right? So then we can talk about base system 3. Similarly, we can talk about base system 16 also, where 16 different combinations are possible, right? And that system is called hexadecimal system. Now, the important conversion which we need to understand is how to convert any number which is given in base R to base 10, right? So we are going to use this generic formula. Let's say this is my number. Okay, so let me give you one number, 136, and this number is in base 5, and I want to convert it into base 10. Then straight away we can't do this. Why? Because once I say base 5, that means only numbers from 0 to 4 are allowed, right? These digits are allowed, 0, 1, 2, 3, 4. But now I'm using 6 here, which is out of scope, right? 6 is greater than base value, which is nothing but 5, right? So this number itself is not valid. So before we perform this conversion, first thing which we need to do is we need to verify whether the number is valid or not. For example, this number is 214 base 5. This is valid. Why? Because numbers which are allowed here must be come from 0 to 4, and 214 belongs to this particular range. So this is fine. So this is the first step. First, we will verify whether the number is valid or not in the underlying base system, and then we will use this particular formula, right? So what is the idea of this formula? In this particular case, we will start with the every time we will start with the least significant digit. Least significant digit is 4. And what we are going to do, we are going to multiply 4 with underlying base, which is nothing but 5 raised to 0, right? So which is 5 raised to 0, which is nothing but 1. So this is my first term. Now I will increase the power of 5, right? So this is, so I can write like this, 214, and this is corresponding to 5 raised to 0. This is corresponding to 5 raised to 1. This is corresponding to 5 raised to 2. And in every step, what I need to do, I need to multiply the digit with the underlying index, and then I need to add all these three terms. So first term is 5 raised to 0 times 4, which is nothing but 4. Second term is 5 raised to 1 times 1, which is nothing but 5. And third term is nothing but 5 raised to 2 times 2, which is nothing but 25 times 2, which is nothing but 50. And if I add these three terms, then I will get one number. This number is nothing but in base 10, right? And similarly, we can do one more exercise. Let's say 2021 base 3, 2021 base 3. So what I will write, 3 raised to 0, 3 raised to 1, 3 raised to 2, 3 raised to 3. And now what I want the final answer in base 10. So what I will do, I will multiply 3 raised to 0 with 1. Then, so this will be my first term, which is nothing but 1. Then I will multiply 3 raised to 1 with 2. So that will be nothing but 6. Second term. Then third term will be 0. I don't need to even multiply. And fourth term is nothing but 3 cube times 2, which is nothing but 54, right? And now I will add these four terms, right? One term is 0, so effectively I am adding 3 only, and this number will appear, that is nothing but in base 10, and so on, right? So this is easy, right? We can do this, but the trickier part is to do the reverse process. So what is the reverse process? Let's say one number is given to us, right, in decimal, and we want to convert it into base R, right? Base R can be anything. For example, in this particular case, let's say 70 is given to us, and we want to convert it into, let's say, base 4. So before we consider this complicated example, let's say one number is given to us, let's say 253, and I want to convert again one number is given to us 253, and we want to convert this number into again base 10 only. I don't want to, I'm not interested in converting it to any other base as of now. I just want to understand the process. How should I proceed? So the idea is, whenever I want to convert this number into base 10, let's say, then instead of multiplication, I should go with division, right? Because the process is reverse now. In the previous case, we were doing, we were converting any number which is in base R into base 10. At that time, we were using multiplication. But now I am interested in the reverse process. So reverse process, if I am doing, then I must use the operation which is of kind of complementary nature in terms of multiplication. So the reverse operation of multiplication is nothing but division. So what we are going to do, let's say I am dividing this, again, I am interested in base 10. So I am dividing this number by base 10. Then I will get 25. 25 times 10 is nothing but 250. The remainder is 3. And I will write down that remainder here. And as you can see, by doing this operation, I have just obtained the very last number which I wanted, which is nothing but 3. Right, so this is like we've already done one program, if you recall, where we were interested in finding out sum of individual digits. There we were performing the similar thing, right? Divided by 10, then one new number will appear, which is nothing but 25. Then we will divide it one more time by 10. This is one possibility. Or what we can do, we can divide the number by 10, then 100, then 1000, and so on, and then we can identify with the help of reminder, we can identify the required digit. So similar thing we are doing here. Let's go further. So if I divide it one more time by 10, then what will happen? 10 times 2 is nothing but 20, and by the remainder I will write down here. So as you can see, I have obtained the second digit now, right? This was my last digit, right? So this is nothing but my least significant bit, or in this particular case, least significant number, and I'm going further now, right? So this is least significant, then I got something, and now if I divide one more time, then division is not possible because the number is anyway smaller. So what I will do, I won't divide it further, and I will say this is my most significant bit, and if I will write these numbers in bottom up manner. So what I got, 2, 5, and 3. So 2, 5, and 3, and this is all I wanted. So now I have got the method, The idea is I need to repeatedly divide the number by base r, and with whatever reminders I get, I will write them down in the reverse order. That will be my answer. But this is with respect to base 10 only. But my interest is to convert this number into some another base. Let's say I want to convert this number into base 4, and the given number is not, let's say, 253, but 74. Sorry, 70, let's say. So then what I need to do, again, I will follow the same process. I will divide 70 by 4. So 17 times 4 is nothing but 68. So remainder is 2. So I will write down remainder here. Okay. And now I will repeat the same process. So 4 times 4 is nothing but 16, right? And the remainder is 1. So I will write down remainder here. Then I will go one more step further, because still it's divisible. So 4 times 1 is nothing but 4, and remainder is 0. But now the moment I obtain a value here which is less than my base, I will stop. So I cannot go further now, because it's not possible to divide 1 by 4. So this is anyway my reminder. So what I need to do, I need to write down these numbers in bottom up manner. So I will get this number 1012, and this number is no, again in base 4, right? So how to verify this? We can again redo the computation from base r to base 10. So what we need to do, if I want to find out its equivalent decimal number, then I will write down like this. This is 4 raised to 0, this is 4 raised to 1, 4 raised to 2, and 4 raised to 3, right? So 4 raised to 0 is nothing but 2 itself. So I will write down 2 into 1. This is my last digit. Then 4 times 1 is nothing but my second last digit. Then I don't need to write down this, because this is anyway 0. So this will 0 times 4 raised to 2, which will become again 0. And finally, I have 4 cube times 1. So 1 into 4 cube, right? And if I sum this up, then this is 4 cube, which is nothing but 64. So 64 plus 0 plus 4 plus 2, which is nothing but again 70. So that means this conversion is correct, right? So what I'm doing effectively here, let's try to analyze this further. So if I write it down one more time here, 1012, and the initial number was 70, then what I am doing effectively, if I divide this number by 4, again, I want my answer in base 4, therefore I'm considering divided it by 4. So if I divide it by 4, then remainder will come as 2. So that remainder is appearing here, right? So this is nothing but the last digit is nothing but modulo 4, I can say, right? Then I will subtract this remainder. So the remaining number is 68, because this 2 is taken care of. So the remaining number is nothing but 68. So what I will do in the next step, I will perform modulo 16 with the remaining number. So if I perform modulo 16, since I'm going left side, so power of 4 will increase. So now I will perform modulo 16. So if I perform modulo 16, then 16 times 4 is nothing but 64, and remainder will be 4, right? So that remainder 4 will appear as 1 here, as you can see here, right? Because what will happen if this is nothing but 4 raised to 0, this is nothing but 4 raised to 1. So my remainder is 4, and I am setting this particular value as 1. So that means that remainder is obtained here, and which is nothing but 4, right? And that is represented by with this setting. In the next step, what will happen? Again, I will move further, and I will consider modulo 64. So I need to subtract 4 here, because it is already taken care. So 64. So if I divide 64 by 64, the remainder will be 0, right? And since this division is possible, the next bit is set, because the next bit is corresponding to 4 raised to cube, right? So that's the alternative view of looking at it. But the main idea is all we need to do is we need to consider the base, and we need to repeatedly do this particular division. We need to write down the underlying reminders, and finally we need to write down the reminders in the reverse order, and we will get the required conversion, right? So we can do one more exercise with the same number. Let's say I want to convert the same number into base 2. So 2 times 35 is nothing but 70. So first will be 0. And this 0 is representing what? That number is divisible by 2. Therefore, this 0 appears. Right? If I start with 71, then what will happen? Instead of this 0, 1 will be there. And that 1 will represent that number is odd. Right? It's not divisible by 2.
Yes, sir.
Right? Okay, let's move further. Now 2 times 17. 17 times 2 is nothing but 34 and remainder is 1. So this 1 is representing that remaining number is not divisible by 2 and so on. And then 2 times 8, which is nothing but 16. Remainder is 1. 2 times 4, remainder is 0. 2 times 2, remainder is 0. 2 times 1, remainder is 0. And now whatever I get here, right, let me write it down, which is nothing but 1 0 0 0 1 1 0. This is nothing but its binary representation. Let's verify. This is 2 raised to 0, this is 2 raised to 1, 2 raised to 2, 2 raised to 3, 2 raised to 4, 2 raised to 5, 2 raised to 6. And 2 raised to 6 is nothing but directly 64. 64 plus, now these bits are 0, so I don't need to consider them. Then finally 2 raised to 2, which is nothing but 4, and 2 raised to 2, which is 2 raised to 1, which is nothing but 2. So if I sum this up, again, this is 0, so I am not considering it. So this is nothing but 70 in base 10, right? So this is correct conversion, right? So I hope this is clear how to convert any number which is given in decimal to any other base system, right? And base system can be anything. It can be base 4, it can be base 8, it can be base 2, it can be even hexadecimal. We'll talk about hexadecimal numbers soon in detail. Okay. So this is the example where we are converting 24 into base 2, right? So what we need to do, repeatedly division by 2, and we will write down the reminders, and then we will write down the reminders in the reverse order, right? And that will be our conversion, right? Now, the next important topic is two different numbering system. The first one is octal and second one is hexadecimal. Let's understand the difference between them, right? So, and also we will learn how to convert binary numbers into this systems directly, right? But we will understand some tricks using which we can directly convert given binary number into octal or base 4 or base 16, right? So in octal system, octal stands for 8, right? So 8 and hexadecimal stands for 16. So what is the meaning of this 8 are required, right? Because 8 is corresponding to 8 different combinations like this: 0 0 0 0 0 1 0 1 0 0 1 1, and then again same four numbers, but instead of this bit 0 we will write down 1, right? So the 1 0 0 1 0 1 1 1 0 and 1 1 1, right? So that means 3 bits are sufficient if I want to represent numbers from 0 to 7, right? So that is nothing but corresponding to octal representation. And similarly, we can talk about hexadecimal representation, where using 4 bits, 16 different combinations will appear from 0 0 0 0 to 1 1 1 1, right? And that is nothing but my hexadecimal system. And in between we can also talk about base 4 system. So again, let's focus on base 4 as of now. What is the idea of base 4? Let's understand it first, and then we'll go to this octal as well as hexadecimal. So base 4 means, again, 4 different combinations are there. Base 4 means 0 to 3. So let's understand base 4 first. So if I write down base is 4, then I know that numbers must appear from 0 to 3. So there are this 4 numbers. If I want to represent using binary digits, then again I am focusing on conversion of base 4 to base 2 only, right? So my focus as of now is how to convert base 4 to binary, right? Base 4 to base 2 or binary. That this is my focus. So in with respect to binary representation, I know 2 bits are sufficient to represent 3 digits: 0 0 0 1 1 0 and 1 1. This 0 0, if I convert it into base 10, then it will be 0. This will be again, this is 2 raised to 0, this is 2 raised to 1. So this is nothing but which number? 2 raised to 0 times 1 plus 0, which is nothing but 1. Again, this number is corresponding to 2, and this number is corresponding to 2 plus 1, which is nothing but 3. So that means using 2 bits, right, I can represent this base 4 system. So let's consider one example. Right? So let's say this is my number. This number is in base 2 and I want to convert it into base 4. Then what I will do, I will split this number into pairs of 2 bits. Why? Because using 2 bits, I can cover all the numbers which are appearing in base 4. Right? This 4 numbers are appearing 0, 1, 2, 3, and these numbers can be covered with the help of only 2 bits. So what I am doing, I am splitting this number into pairs of 2, 2, and I will go from left to right, and I will write down the equivalent value for uh, each pair. So for the very first pair, the number is 0, 0, and its equivalent value is 0. So I will write down 0 here. For the next pair, the pair is 0, 1, and its corresponding value in base 4 system is nothing but 1. So I will write down 1 here. For the next pair, the value is 1, 1, and corresponding um, a value in base 4 system is nothing but 3. So I will write down 3 here. And for the last pair, the number is 1, 0, and its corresponding value in base 4 is nothing but 2. So I will write down 2 here. So directly I can get this particular answer, which is nothing but in base 4. You can verify these two numbers are equivalent. What you can do, you can convert this into base 10. You can convert this into base 10. You will get the same answer, right? So now the question is why this works. So the idea is whenever we are talking about base 2 system, then as we have noticed earlier, in base 2 system, this is happening 2 raised to 0, 2 raised to 1, 2 raised to 2, 2 raised to 3, and so on. So whenever I consider two bits which are coming in succession, then I am basically considering this four combinations only, right? Which are nothing but 0, 0, 0, 1, 1, 0, and 1, 1. These are the four possibilities with respect to any two consecutive bits, and only those four possibilities are required whenever I talk about base 4. So similar kind of trick can be possible when we club one more bit together, which is nothing but whenever we talk about 3 bits. So 3 bits, using 3 bits, as we have discussed earlier, we can represent 8 different combinations from 0 to 7, and this is corresponding to nothing but octal system. So same trick we can use to convert any binary number into octal. And also if I combine one more bit, then the system will become hexadecimal, because now with the help of 4 bits I can represent 16 different combinations starting from 00000 to 1111, right? And those numbers will be corresponding to hexadecimal system. So we can also convert any binary number into hexadecimal number if we consider grouping of 4 digits, 4 bits, not 2, right? So with 2 bits grouping we can obtain base 4 representation. With 3 bits, we can obtain representation of octal system, which is nothing but base 8. And with 4 bits of grouping, we can obtain representation for hexadecimal system. Okay, so let's consider this in detail. So now one question can come, that what will happen if last pair is incomplete, right? Because it may possible that numbers are not total number of bits which are present are not multiple of 3. For let's say in this example we want to convert this number into base 8, then I need to consider grouping of 3 bits. So first group is this, second group is this, but third group is incomplete. So what we can do, we can append 1 0 here, right? So this 0 will complete this particular group also, and then we can write down its equivalent value in base 8, right? So first group is 1 0 0, and all we need to do is we need to write down its representation in base 8, right? So 1 0 0, so this is 2 raised to 0, this is 2 raised to 1, and this is 2 raised to 2. So its representation is nothing but 4 only. So we'll write down 4 here. Again, if we go to 110, then 110 is nothing but 2 raised to 1 plus 2 raised to 2, which is nothing but 4 plus 2, which is nothing but 6. So we can write down 6 here. And if we go to the very last group, which is nothing but 010, then 010 is nothing but 2 raised to 1, right? All other bits are 0. So we can straight away say it's 2. So all we need to do is we need to write down the equivalent value in base 8 for all these 3 groups. So my final answer is nothing but 264 in base 8, right? And same thing we can do with respect to base 16 also. But in base 16, there are some issues. What are the issues? Let's say whenever I want to represent anything with base 16, then basically this 0 to 15, these digits are allowed. But now what will happen if my number is 10? So do I need to consider this 10 as 10, or it is 1? This is I can consider this 10 as 10 also, or I can consider this 10 as sequence of 1 and then 0 also, right? So we don't know. If I write down 10 in base 16, then we don't know whether it's a single number or it's a combination of two numbers, because already these digits are allowed: 0, 1, 2, 3, 4, 5, 6, up to let's say 9, then 10, then 11, then 12, right? So similarly, whenever I write down 11, then I don't know whether it's 1 after 1 or it's 11. So in order to solve these issues, what we are going to do, we need to somehow distinguish this 10, which is nothing but actually 10, with 10. So what we are going to do, we are going to assign different letters to numbers which are appearing after 9, so that we can avoid this ambiguity, right? Otherwise, what will happen whenever I write down 12, we don't know whether it's 12 as a digit or it's 1 after 2, whether it's a single digit or double digit, we don't know. So therefore, to avoid this confusion, we have assigned letters to digits which are appearing after 9. So what we are going to do, and generally we start letters from A. So what we are going to do, we will say this as A, not as 10. So whenever I say A in base 16, that means I'm talking about 10. Whenever I say B in base 16, then I'm talking about 11. Whenever I say C, then I'm talking about 12. Right? So that I can distinguish between these two cases. And now if I write 1, 2, then I'm talking about 1 after 2. And if I write down C, then I'm talking about 12. Right? So in order to so that's the objective of this digits. Right? So now if I go further, then for D we have 13. Right? So for 13 we are having D. Then E 14, and the last one is 15, because in base 16 I cannot go um, up to 16. I need to stop at 15 only, because only 0 to 15, this 16 different combinations are allowed in base 16. So I need to stop here. So I am going up to F only, right? So in base 16 system, basically I am allowing these numbers, as you can see here, right? From up to 9, it's fine. It's 9 in hexadecimal. But now for 10, I am using A. For 11, I am using B. For 12, I am using C. For 13, I am using D. For 14, I'm using E, and for 15, I'm using F, right? And anyway, we know how to convert binary into base 4, octal, as well as hexa, right? But this table just contains all the numbers from 0 to 15 and their representation in terms of binary, base 4, octal, and hexa. Okay. Now let's continue. Our objective is to convert base 2 number into base 16 number. How to do it? Again, what we need to do, we need to consider groups of 4 bits now, not 3, because now my system is hexa, not octal. So this is my first group, right? And this number is corresponding to 4. So I will just write down 4 here. And this number, if I consider 1011, so let me calculate its equivalent value. So this is 2 raised to 0, this is 2 raised to 1, this is 2 raised to 2, this is 2 raised to 3. This is 8 plus 2 plus 1, which is nothing but 11. But in hexa, I cannot write 11 directly. I need to consider its equivalent letter, which is nothing but B. So I will write down B here. So now this is nothing but B4, and underlying base system is 16. The moment I see these letters, I must understand that I am talking about hexadecimal system only, right? So you can see this is nothing but hexadecimal representation. This is octal representation. This is base 4 representation. And finally, we have nothing but binary representation, right? So the advantage of this representations are mainly in terms of uh, saving, saving memory, right? Because if I want to represent any number in binary, then many bits are required. But the same number can be represented effectively if I use hexadecimal, because roughly what will happen, 75% of the storage will be saved, because for each 4 digits of binary I am using 1 digit of hexadecimal, right? So it's a massive massive improvement in terms of storage, right? Okay. And again, we can do this conversion also, where one number is given in decimal, and we need to consider its binary value, base 4 value, octal value, and hexadecimal. Similarly, one number is given in binary, and then we need to consider all other, convert it into all other forms, and so on.
Thank you. Subscribe to my channel for more videos.